All right, can you all hear me okay? Just chat if you can, please, just so it's clear and we can get going. Awesome. All right, folks. Well, good morning or good afternoon or evening, depending where you are in the world. I just wanted to pop this session just to hopefully help you guys with some last minute preparation for the multiple choice test. Now, this is obviously your last exam of this school year, academic year, anyway. But hopefully, this will serve you well, obviously for this test, but also going forward into your A2 year. For those of you that are doing that, and if anyone is doing anything different, then please do let me know what your plans are sort of beyond for next year, because I am trying to plan how I can be helpful to those of you that continuing next year. So yeah, if you can respond to any of the emails I send out, I'm just going to be trying to plan what I'm doing as of September. But yeah, let's get into it. So I really didn't want to focus in today just on actual parts of the content specifically, just because really by the time you get to this point, generally speaking, students have a pretty good grasp of the concept, but sometimes it is really technique that lets them down in the multiple choice. So I just wanted to focus mainly on the technique, which will then apply to some questions. If you don't already, I would recommend that you have a calculator, a notepad, or paper in front of you, just so that you can work along as we go through these. So we're going to do 4 or 5 examples within the session that I've planned. Then at the end, if you guys have any others that you want me to take a look at with you, then we'll have a little bit of time for questions at the end. But yeah, I really want to just focus in on how, with only a few days to go, you can change your technique if necessary. Maybe you're already doing everything that I'm about to tell you, which would be fantastic if you are. But just slight tweaks in the technique and how you approach these questions really can make the difference, and save you dropping just a couple of silly marks. Be the difference between an A and an A star in the end of it. So that's really something that we want to take advantage of. So let's jump into it. So if we look at just what I've broken this down to initially, so we've got setting a positive direction. That is specifically to do with anything vector related. We need to make sure that we are consistent with our directions. It doesn't actually matter which direction you set as positive. We will get into this in more depth in a moment. But as long as you're consistent, then that will allow you to not drop these silly marks because you haven't taken into account a negative or something like that. The second one is knowing the exact wording of definitions, especially Cambridge wise. Have you seen enough of the mark schemes to know exactly what the definition is in case of any questions where it says, suggest the correct of these 4 or whatever. If you don't know the exact definition, then they're all going to sort of merge and seem like almost the same thing that they're saying. There are only real subtle differences. That's why we need to be really clear on the exact definitions. I also, when we get to that point, I will drop a link in the chat where something will help you practice this. Making sure that we're always converting our anything that we're given, any quantity, into the SI unit. But specifically with the prefixes, we just need to get into that habit of, if I see 240 milliamps, then straight away how I'm putting that into my calculator, or how I even think about it, is 240 times 10 to the minus 3 and I'll just put that into my calculator straight away. I won't try to convert between milliamps and amps or kilowatts and watts, anything like that. I won't do that conversion myself personally before putting it into the equation, which is probably how I would have done it at GCSE, or how I do teach it at GCSE, to convert it beforehand. How I generally teach it at A level is to just be clear on how you're going to put that into your calculator. It does not need to be correct standard form to put it into your calculator with a times 10 to the and then a power. And then finally, don't ignore internal resistance. That is specific to some of the electricity questions. So we'll jump into that. Okay, so the first, I just want to really get these habits nailed down so that you're clear on what you should and shouldn't be doing. And if you can then be consistent with this, you'll notice that it eliminates a lot of your small little errors that are costing you marks. So momentum and force as examples obviously are vectors, but this can be for any vector additions really. One of the most important things is setting a direction to be positive before you really jump into it anymore. Do that to start with, then think about the question. Okay, so I would always put an arrow, let's say to the right, and just put plus VE to mean positive, or right positive above it, something like that, just so that you're really clear. If there's a vertical and a horizontal component, then you should do one vertical arrow and one horizontal arrow to suggest, let's say, upwards is positive and to the right is positive. If we know that, then obviously to the left is negative and downwards is negative. We're clear, and we're going to keep that same convention. The other thing here that I've shown is just if we are having to resolve a vector into components, a huge sort of student errors here is mixing them up which way around to go. Obviously, we can always go back to soft tower. If this is our angle here, then soft will be opposite of our hypotenuse, hence that would be sine if we're looking at the vertical, and cos would obviously be for the ka, the adjacent of the hypotenuse, and hence this one will give us the horizontal if we go for the cosine. All right, so we need to be really clear on that. That is something, and I forgot to mention in my little intro, I have put all of this together really and designed this session from my research and analysis of the examiner style, the examiner reports, sorry, of the last 15 series, which goes back all the way to the March series in 2021. So these are really the biggest errors, the biggest misconceptions, or the traps that they tend to set, that obviously people do get stuck into. All right, so let's jump into the first question. I'm going to give you, we do have probably, it's just under 2 minutes per question. I think 1 minute 50 per question for the AS paper one. So I'll give you about 1.5 minutes to have a look at this question. Another thing that I would recommend doing is ignoring the 4 answers that it gives you initially. I would work this out just as you would if it was on the theory paper. You would obviously show all your work in, you would get to a final answer, and then you would make sure it's got the right units. Now in this, we have got options, but it is a well documented issue that sometimes students try to just plug in the values that they're given. So they'll try it with A, then they'll try it with B, then they'll try it with C. And they're basically doing trial and error to see which one might come out as, where they can get back to one of the numbers they're given in the question, for example. That is not the best approach in my experience. Try to answer the question without the answers. And then, of course, when you think you've got to a final answer, and then you see, oh, that is the options, let's say, oh, that is D, brilliant. Then you're confident because you got there without being swayed by any of those answers. Is that better? I just saw a message saying, could I zoom in? So hopefully that works. Can I give you about 1 more minute to see if you can get to an answer on that one, and then we'll work through it with the support and how exactly I would present this. Again, making sure that we are clear on which direction we are saying is positive. It doesn't matter whether you choose to the left or to the right. You are consistent with that signing, and as long as you are, you will end up with the same answer regardless. All right, just drop your answer in the chat if you get to an answer and you think that you've got an answer that you would choose. A, B, C, or D, and then we will go through it and see if we manage to get that. All right, so you're going for C. Anyone else got an answer for me? Just drop it in the chat if you do. All right. Well, we seem to be in agreement, so that's great. Let's see then how exactly I would approach this one. All right. So, you guys maybe said that you were going to set the positive direction as right. I actually said, all right, let's take L's initial direction as positive. So we're taking to the left. So that's how I just show it. I just draw an arrow to the left and right plus VE, so positive. So that's my note to myself. That's not going to be marked by anyone. That's my note to me to say, okay, anything to the left is going to be positive. That means anything that's to the right is obviously going to be negative, and that just makes me clear on that from the start. Okay, so if it says during the collision, the blocks are in contact with each other for a time of 0.084 seconds, we've obviously got the momentums of the blocks. K is moving to the right with 0.72 kilogram meters per second, and L is to the left with 0.46 kilogram meters per second. So it says after the collision, block separate, block L moves back along its original path with a momentum of 0.12 kilogram meters per second. If it is going back along its original path, that tells me it's in the opposite direction. And if we're saying to the left is positive, this 0.12 kilogram per second is actually going to be negative. Okay, so this is what we're looking at. We're looking at the change in momentum, which is delta P. Okay, is equal to the final minus the initial. Okay, so the final momentum in this case, taking into account our signs and our direction, is minus 0.12 minus 0.46, positive 0.46. Okay. So you're going to end up with 0.58 kilogram meters per second as the magnitude. The minus just tells us that it is going in the opposite direction to my to the way that I've flagged it at the start. Again, if you'd done this the opposite way around and you'd said that positive was to the right, then you would end up with 0.12 minus 0.46, and therefore you'd end up with your magnitude as 0.58 kilogram meters per second once again. So then if we want to look at what the force is, now that we've got the actual change in momentum, note that that's really where the main error would be in this one. If someone has maybe just looked at the difference in the magnitudes of the momentum, so 0.46 minus 0.12 would give you 0.34, and then 0.34 over 0.084 would give you one of the other answers. But how we actually obviously need to do it is take our change in momentum, the magnitude of 0.58, divide by the time that force is going to be applied for. That is then going to come out as 6.9 Newton. Okay, making sure that we do get all the way to the end here, and you do get to a force rather than this one. It's not the case, but sometimes they might leave 0.58 as one of the answers, so that when you get to that point, you're like, oh, I've got to the answer. I've seen that that's one of the answers. It must be right. No, that is another trap for you. So what did the examiner report say on this? It said option B was the most popular incorrect option, with candidates neglecting to account for the vector nature of momentum, and so finding the difference in the magnitude of block L's momentum, not the difference in momentum. The difference in the magnitude of the momentums obviously doesn't take into account the sign. If we are taking into account the directions, then it is a bigger change in momentum, because of course it had to lose all of that 0.46 kilogram meters per second and then gain 0.12 kilogram meters per second in the opposite direction. If you think about it on a number line, it goes all the way down to 0 and then goes up in the other direction. It's obviously a bigger change in than just the change in the magnitudes. All right, so the answer is C. You guys got it correct, so we're very well done. Making sure that we're not, falling into that trap. Making sure that we have the reversal means that it's 0.46 plus the 0.12, and we are going to end up using the correct change in momentum and therefore get the correct force. All right, so on to the second one. Using the exact syllabus wording. Now, I did mention that I would share the link at this point, just because I think this is something that is quite commonly messed up. So I've made a little definitions and formula trainer, which I've just linked in the chat. So that one might help you with just being able to drill exactly whichever formulas and definitions you want to, whether you want to do that by individual topic area, or if you want to just have a go at doing all of them at once, all of them just definitions, or all just formulas, or both. So hopefully that is useful for you. I can just maybe show you on here what the actual what it actually looks like. Just one moment. Oh, my bad. 1 second. This is my first time doing a live stream, so I'm not particularly familiar with exactly how this all works. Actually, let's just carry on. I'll bring that up when I share my screen on the presentation. So, using the exact syllabus word, as an example, acceleration is the rate of change of velocity. That means that change in velocity per unit time, and that is the rate, because anything per unit time is a rate, just like power is the rate of change or of transfer of energy. Okay, so acceleration is the rate of change of velocity. Now, let's just be really clear. When it says not rate of change of velocity per unit time, because if you say rate of change of velocity, you've already defined acceleration, and then acceleration per unit time is the same as saying the rate of change of acceleration. So that would actually be jerk, which is the derivative of acceleration, just like velocity is the first derivative of displacement. Um, acceleration is the first derivative of velocity, and so on and so forth. It goes jerk, and then actually snap, crackle, and pop. If you've ever looked into that. But yeah, just be really careful with the terminology. Now, you don't want to sort of double define something. So, rate of change of velocity is already change of velocity per unit time. If you then say per unit time afterwards, you're actually defining a different quantity. So, we need to be really careful with that. Now, EMF is the work done per unit charge passing through, let's say, the cell or battery, but it is work done specifically by the source, so by the power source, whether that be a cell, like I say, power supply, whatever it is. EMF is the is from anything that is supplying energy to the circuit. So the definition specifically is the work done per unit charge on the chargers, so it's by the source. Okay, whereas PD, potential difference, it, it's not a potential rise, it's not where the energy is being given to the circuit or the charge in the circuit. This is the work done per unit charge between 2 points in a component or in a circuit. Okay. So potential difference is specifically it is the chargers doing work. That means that they are losing energy as opposed to getting with EMF. Okay. So let's try and put that into practice with this question, which is question 36 from, let me try and recall which paper that one's from. I think it's from November 25, paper 12. All right, so I'll just zoom in on that one for you. And yes, Lambda Lab, yeah, you're right. I do have one for AS and one for A2 definitions. So yeah, for those of you that are continuing on to A2 next year, that should be really helpful for you there as well. Also, I am, like I said, like I mentioned before, I am sort of gearing up over summer to produce something. I don't know exactly what it looks like yet, but something for next year that hopefully will be helpful for anyone studying A-level physics. So yeah, if you have ideas on that, what would be useful for you or suggestions, I'm all ears. So yeah, you can reply to any of the emails or even drop it in the chat here, if that's the case. All right, so let me read this out for you in case anyone that would be helpful for anyone. So the electromotive force EMF of a cell is 6 volts. It has negligible internal resistance and is connected across a resistor. Potential difference of PD across the resistor is also 6 volts. The EMF and PD have the same numerical value but represent different processes. Which statement about the different processes is correct? Okay, so this kind of question, very wordy. That means you need to be really scrutinizing what are the differences here between the different options. You need to be really clear. I would maybe think about highlighting the important parts of each of these so that you're not then going to sort of they're not going to just merge into one. You can highlight exactly what are the differences on each of these. So A says the EMF is the energy transferred from chemical energy to electrical energy in the cell, and the PD is the energy transferred from electrical energy to thermal energy in the resistor. B says PD is energy transferred from chemical to electrical in the cell, and EMF is energy from electrical to thermal in the resistor. What's the difference between those two? Oh yeah, it's just swap PD and EMF around, right? And then C says EMF is the energy transferred per unit charge from chemical energy to electrical energy in the cell, and PD is transferred from thermal in the resistor. And then again, it's those two flipped. So if you're not clear on the definitions here, and if I hadn't just shown you them moments before, this might be quite tricky for you, right? But as always, we have to try. If you don't know the answer, just by reading through them and going, "Oh yeah, okay, I know it's that one," which hopefully you would if you had a really good grasp of the syllabus and your definitions and everything like that. But often that's not the case, and we need to understand what our process should be if we're not 100% sure just from reading the options. Okay. Now, again, I would probably, before I even start reading these, I would have to think about, okay, what is what is EMF and what is PD, and get it clear in my head, and then read through the option. Now, there's two, once again, that we can get rid of before we really jump into it. Now, depending which point you have in your mind, you'll be able to eliminate two. There's two different points to think about, and if you think about both of them, then naturally you will eliminate the other three and only have one left. So can someone in the chat tell me why or on some kind of condition how you can delete two of the options? And if you can say what that condition is, oh, I can get rid of this and this because, and say what it is, then that's really the thinking that will allow you to, even if you don't know the answer before you select it, you would be able to narrow it down to two options and then have an educated guess at that point, as opposed to just simply having to guess between the four. All right, so I've got a couple of people saying that they think it's C. What? Okay, here we go. So PD is across a load / component, EMF from cell. So B and D eliminated. Very well done. So if we are clear on that, if we're clear on the EMF being a potential rise, I like to call it. So think about it being a step up, if you like, in terms of energy as the charge goes through the cell. That means it gains energy. That means work is done on the charge. When it goes through a resistor, it's going to drop. That means the opposite. That means that it is giving up energy. Okay. So as we said, we can eliminate B and D for that reason. Okay. Because we know that it's the wrong way around. Okay. Now, then when we look at, okay, well, we've got A and C left then. How do we want to look at these ones and think, okay, how do I get rid of one of these options? Well, one of them has per unit charge, one of them doesn't. Now we know, if we know our definitions and we're clear on them, or if you just know the formula, then you know it has to be per unit charge. Okay, it is not just simply the energy. If it was energy, it would have joules as your unit. It doesn't. It has volts. We know that the that potential difference is work done per unit charge. We know that EMF is work done per unit charge. Whether that work is done by or on the charges decides whether it's EMF or PD. So if we then look, okay, we've eliminated B and D, then if we look at which one of these it must be, it's the one that has per unit charge in that definition. Okay, so C keeps per unit charge, and it's the right way around, if I can speak. So EMF, energy per unit charge put in by the source. PD is energy per unit charge taken out in a component. The per unit charge part is very important because otherwise it's not defining either of them. And then obviously making sure that we know that a cell is obviously going to put in energy, a resistor is going to take away. So it must be that way around. Okay, so it's important to carefully read the text of the question, first of all, but also, obviously, of the options. Candidates should be familiar with the definitions of physical quantities in the syllabus. Like I say, that link to the trainer should help you a lot with that kind of thing. So C, A drops per unit charge. It defines energy, not energy per unit charge, so not EMF or PD. Therefore, we go with C. All right, so habit number 3. Mining prefixes and powers. Okay, now there's sort of twofold here. Now, one is just to obviously be very clear on what the prefixes are. So milli being 10 times to the minus 3, mega being 10 times to the 6. We should know those. They should be quite straightforward for us, almost second nature really by now. But one thing that still continually trips students up is whenever we have centimeter, like when we have an area or if we have a volume. Okay. So 1 centimeter squared going to meters squared. Well, first of all, if we were going from centimeters to meters, we know that we divide by 100 because 100 centimeters is 1 meter, right? So centimeters to meters, you just divide by 100. But if you are talking about a square, we're talking about the area, then there's a 1 to 100 ratio in one direction, but there's the same 1 to 100 ratio in the other direction. So it is in 2 dimensions. So rather than divide by 100, we would have to divide by 100 for one dimension, and then also divide by 100 for the other dimension. So rather than 1 centimeter squared being 10 to the minus 2 meters squared, it ends up being 10 to the minus 4 meters squared, right? So if you know how to convert between the two basic units, so centimeters to meters or meters to centimeters or whatever it happens to be, meters to nanometers, then if it's squared, then you just do the multiplier squared. If it is cubed, again, the multiplier, you cube it. Okay, so that's just to make sure that we're really clear on that. We don't want you to be messing up on your calculations and just having power of 10 errors for that reason. So yeah, be really clear on that. Also, as I mentioned before, if I ever see 25.2 megawatts, all I do is put 25.2 times 10 to the 6 and press equals in my calculator. Then it's already there in it'll put it into normal standard form. I did not need to do that for myself in my head. That is when you might accidentally move in the wrong direction, and again, you're going to end up with a power of 10 error. Okay, so make sure that we are really clear on this. Also, for diffraction grating, if you're told how many lines per millimeter, we have to be lines per meter. So we need to again be really careful on that front. So let's have a look at that one. Light of wavelength 680 nanometers is incident normally on a diffraction grating with 450 lines per millimeter. What is the angle of diffraction of the second order maximum in the diffraction pattern that is produced? I'll just give you one more minute for those of you that are finishing that one off. I can see one of you in the chat has an answer. Someone else agreeing with them. That's always good. All right, let's have a look at this one then. So, if we have 450 lines per millimeter, obviously the main thing here is to make sure that we convert this correctly before we start plugging into our formula. Okay, so if we find D, which obviously is 1 over n first, but needs to be in meters. Okay, so if we convert that, then you should get 4.5 times 10 to the 5 lines per meter. Okay, 450 lines per millimeter should be 4.5 times 10 to the 5 meters. Sorry, lines per meter. Okay, and then let's look at the spacing then. So obviously, once we know how many lines per meter, we then do 1 over that number to give us what the actual spacing of the lines is. And so we get 2.22 times 10 to the minus 6 in this case. Okay. We then need to obviously use our formula. So d sine theta is equal to n lambda. And we need to make sure that we're looking at the correct order. It says the second order maximum. All right, so n is going to equal 2. All right, so sine theta is equal to 2 times by 680 times 10 to the power of minus 9, because that's the nanometer. That's once again, we have got a prefix in there. We need to be making sure that we are correctly having that as minus 9. Divided by our 2.2 times 10 to the minus 6 should give us 0.612. If we then do the inverse sine, you should get 38 degrees. So D is the correct answer. Now, the examiner report said candidates should be familiar in the use of diffraction gradient equation, including presenting a number of lines per millimeter instead of a line spacing. Okay, and giving angles between second and third order maxima. So answer D, 38 degrees. That's a good point, actually. When this mentioned giving angles between second and third order maxima, this one just said angle of diffraction of the second order. Sometimes you do get questions where you have to give the angle that would be between the second orders. Okay, so that would actually be double this answer if you were looking at if straight through here, this angle is what we just worked out. But obviously, if you're looking at between the second orders, so either side, then the angle between them would be double whatever you get out of this equation. That is a good one to just note as well, because that does come up reasonably often. Okay, any questions on that before we move on? I think you guys seem to get the right answer, so I won't labor the point. So habit number 4. This is a big one as well that came up through the analysis that I did. Once again, just to remind you, I will be sending that out. In fact, it's already scheduled to send for those of you that have signed up through the landing page and you've been receiving my emails. If you have done that, that's absolutely fine. You don't need to do anything else. If you haven't and you've found your way to this stream through a different link and you haven't signed up for the emails, that won't be delivered to you unless you sign up at the end. I will make sure I've dropped it in the chat. But yeah, so that's the full breakdown and analysis of the previous 15 series of these papers. All right, last habit that I'm going to talk to you about then. It says don't ignore the internal resistance. So cell has a resistance too. We know this. It is called the internal resistance. Generally, when you have a diagram, a circuit diagram, you're going to have a dashed box around the cell that shows a small resistor in there, which is small r, for the resistance. Obviously, you should be familiar with those types of questions, but please, 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 please do not forget about that, because this one is an example of how that can get you. Right, so again, I'll give you about a minute and a half to have a look at this one, and then we'll jump into me solving it for you or discussing how we go about solving it. And then I'll hand over to you guys if you've got any questions that you'd like me to go through with you quickly before we finish up today. Then you can send through those. All right, folks, let's have a look at this one then. So we've got internal resistance of 1.0 R. Then we have a variable resistor with an initial resistance of 2.0 R. Okay. The current in the cell is I1 and the terminal PD across the cell is V1. Okay. The variable resistance now adjusted to a new resistance of 4R, and it says the new current in the cell and the new terminal PD across the cell. All right. So what we need to think about here is obviously the variable resistor, the resistance has doubled. Okay. So straight away, that really sort of tries to tempt students into going for A or B. Okay. Which would be wrong. The reason that would be wrong is because it, of course, isn't going to exactly half the current, because that doesn't take into account all of the resistance. The total resistance initially is 1 plus 2, so 3 of them being in series. Afterwards, you've got 1 plus 4, so it's 5, okay? 5R. So it went from 3R to 5R. It certainly did not double, okay? The resistance did not double, so the current must not have halved. So A and B are out straight away. Obviously, given that C and D are both 0.6 I1, that shows that that must be the correct answer, okay? And it's also definitely true, because if you think of the numbers I just mentioned, we've got the resistance of 3R going up to a resistance of 5R, 3/5 is 0.6. Okay, so that's where we obviously say, okay, it is going to be C or D. Which one? Sorry, that's what I mentioned before. Which one is it going to be in terms of the terminal PD? Well, this one's an interesting one because if there is a smaller current than before, that means that the lost volts, as in I small r, which in this case is I times 1 big R, that is going to come out as a smaller number for the lost volts than before. Okay? Because the current is smaller, that means that the dissipation of power in that internal resistor is going to be less. So that shows us that it's not going to be C, because it's not going to be just the same. It's actually going to be increased because it's losing less to that internal resistance. Therefore, your terminal PD is going to be larger. Okay. So, what did the examiner report say? Obviously, that meant that the answer was D. It says they could recognize that doubling the external resistance did not quite double the total resistance. The new current would be slightly more than half of the original current, eliminating A and B as options. That is literally what we just went through. But the other part is making that next leap that, okay, if the current is less, there's going to be less power dissipated or less lost to the system, which means that our answer should be D. All right, folks. So that is the 4 sort of main technique traps I wanted to discuss with you today. If you have any questions you want to drop in the chat, I'm more than happy to go through a few. And if not, then yeah, I wish you all the best for your exam on Wednesday. I think it is. Is it Wednesday? Tuesday? Wednesday. Yeah, and hopefully I will see you again next year after you continue on into A2. But yeah, do drop me. I'll stay on for another minutes if you want to drop any paper references to questions that you'd like me to go through with you. I'm happy to do that. And if not, then I'll just show you on here. If you follow there, then that will mean that you get the replay for this straight to your inbox, as well as the breakdown that I've produced that will be going out as a free little thank you resource. There's also a one-page version if you don't want to read the whole breakdown, if it feels a bit too close to be spending 20 minutes reading through a document. If you just want to get the sort of cliff notes to just apply real quickly, then you can do that as well. Can we email you questions regarding other papers too? You can always drop me an email. I will do my best to get back to you if you do that. When you say, "Are you on the support?" I'm not entirely sure which form you're talking about there. So at the moment, it appears not, but it may be something that I can join. I presume this is your last exam for physics for this year, though, right? Let me just, while I see if anyone does want to share, just see if I can. if I can just show you that document. Let's have a look. All right, so let's we can have a quick look at what the guide looks like. Oh, nice one. It's good to have you along, Lambda Lab. So this is the guide that I've put together. Um, multiple choice survival guide. It says how to use it. Not a content summary. You have a textbook for that. Da 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 da. Um, paper at a glance, and then really specifically what I think is important about this and what is useful is that it's flagging per series. So how many series of the 15 that I've been analyzing, how many times did this come up? Obviously, the ones towards the start are real heavy weighted. They are really why I've chosen to talk about the things that I have during this session. But yeah, I'll share that with anyone that has signed up via the web link. And hopefully that is helpful to anyone, whether that be a student or a teacher that can share it with their own students. You're more than welcome to distribute that. Which link are you struggling with? Sorry. Is that the link you meant? So if you follow that link and you then put in your email if you haven't already, then you will receive this free guide that I've done the breakdown for. If you train them for 1 minute per 1 minute 30 seconds per question, yes. Yes, yeah, that's a good idea. I would say, yeah, saving sort of 20 seconds per question if you can. Um, then yeah, just gives you that time at the end so that you're not sort of stressed. Um, Getting to the end of the paper exactly on time, I would try to work towards yeah, being a little bit ahead of time, just so that they can sort of go through with this kind of checklist in their mind, um, and really check that they haven't made any of these mistakes that really trip people up every year. Awesome. All right. That is all I've got time for today. But yeah, any questions that anyone has, feel free to shoot me an email. And thank you very much for joining. Hope that has been helpful for everyone. All right. Good luck on Wednesday, those of you sitting the paper. And let me know if there's anything further I can help with going forward. Take care.